like we listen to you like
Oh,
after
okay.
like 2 or
Okay.
3 seconds.
There is a lag. Siddharth, you always come defending your class. No problem. It's okay. Okay, boys, but be on time. Already for us to move from one class to other class, it takes few minutes, right? In spite of that, if you lose classes, now look at the tabular column, boys. The coefficient of linear expansion of different substances are
Ma'am, do we
being
write
given.
this?
No, no, no need, no need. No, I'm just giving you an example. You should know the coefficient of linear expansion of certain substances are given, which means let us take aluminium, brass, copper, iron, lead, whatever material. Let the dimensions of all the material be the same, and these materials are being heated to a temperature of say 1 degree centigrade. What might be the expansion of all these materials? Their initial conditions, which means their dimensions, their initial temperature are the same, and the heat energy what you are going to supply and the duration for which the heat energy is being supplied, all these experimental conditions are the same. But can you see the values are different, which means different material undergo different expansion. So the one which has a larger value of coefficient of linear expansion, which one is having a larger value of coefficient of linear expansion? Is it zinc?
Yes,
Right?
ma'am.
So we can say zinc undergoes a large amount of thermal expansion compared to the other materials, which is going to go for the least. It is glass. That's what glass can withstand high temperature. Because
Ma'am,
this
what
is one
about
type.
ice? Ice, it says
Ice
51.
51 degrees. Yeah. Have you heard about latent heat? So when you supply heat energy, no hidden heat, right, boys? You can't see the change in temperature. Have you heard about latent heat? See, when you supply heat energy to ice, naturally from solid state, it has to move on to liquid state. Suppose you have an ice cube, right? Say the temperature is 0 degree centigrade. You are supplying heat energy. So as you supply heat energy, slowly it will be converted to liquid state, but the temperature remains the constant. The temperature is, you are supplying heat energy, boys. You are supplying heat energy, but your solid, the ice in the solid state now will be converted to the liquid state. You expect the temperature to rise, but the temperature will not rise. What is the reason for that? What's the reason for that, boys?
Ma'am,
Ice,
because
say,
it needs heat energy to break the intermolecular forces.
okay, it needs heat energy to break. In other words, what we say is that all the heat energy is used to get it transferred from solid state to the liquid state. Once your ice has been completely transferred to the liquid state, then thereupon you can see the rise in temperature. So this hidden heat, right, we call it as latent heat. So chemistry would have learned about latent heat, right, boys? So linear expansion we have completed. Next we'll go for superficial expansion, which means you're considering a
Ma'am,
metal sheet is
where
boss.
should you write this?
Yeah, next one is superficial expansion,
Okay, ma'am.
right? Subheading coefficient of superficial expansion. Coefficient, the value of coefficient of superficial expansion tells you which material can undergo a larger extent of surface expansion on heating. Are you clear, boys? Coefficient of superficial expansion is a quantity, it's a physical quantity which tells you which you can have coefficient of superficial expansion. Already they would have calculated under the experiment, they would have calculated by performing experiments for different materials. So this value gives you an idea to what extent a material or a metal can undergo expansion in its surface area on heating. So we have to derive an expression for it. What is superficial expansion? increase in area on heating is called superficial expansion. So now let us consider the initial dimension. Now let us consider a metal in the form of a thin sheet. We call this as a lamina. We are considering a metal in the form of a thin sheet. Now this metal has an surface area A1 maintained at a temperature of T1 degree centigrade. Now you are going to supply heat energy so that the metal surface gets heated up and it begins to expand. Now after some time, let the new area be equal to A2 and the new temperature be equal to T2. Is that clear, boys? So now the area has been increased. I can write A1 is the initial area. A2 is, you can just have a notation. A1 is the initial area. A2 is the final area. Delta A, which is equal to A2 minus A1, will be change in the area. Delta T is the change in temperature. T1 is initial temperature. T2 is your final temperature. If you can't write it in a paragraph, you can specify A1 original area, A2 final area. Delta A is change in area. T1 is initial temperature. T2 is your final temperature. Then delta T, which is equal to T2 minus T1 is change in temperature. Here the coefficient of superficial expansion is beta. Clear, boys?
Ma'am, so instead
Derek,
of alpha, it
have you
should be
joined the class? Yes, boys. No need for this. We'll derive. Derek, have you joined the class? Dheeraj? Derek and Dheeraj?
Yes, ma'am.
Derek?
Yes,
Derek
ma'am.
and Dheeraj? Okay. Did you miss the bus, Derek
No.
or Dheeraj? Huh? Why so late, boys?
Ma'am, I joined before. I was 4 minutes late.
Okay,
Not
sorry.
now.
Sorry.
Ma'am, the meeting didn't show up, so I just joined 2 minutes
Okay,
later.
okay. Sorry, boys. Sorry. Please do right. Boys, if at all I say something, don't take it right to your heart. No, the problem is your portion, your what the subject is so vast, so many things you are learning this academic year. It's we understand it's very tough for as a student. So if I keep checking your attendance, already shifting from one class to other class, we need to take it takes time, right? So in spite of that, checking your attendance and calling you whether you have understood our concept, see how difficult it is for us. Don't waste time, boys. I have to do numericals. Now start writing A1 initial area, A2 final area, delta A is change in area, T1 initial temperature, T2 final temperature, delta T is change in temperature, beta is coefficient of superficial expansion, T1 initial temperature, T2 final temperature, delta T is change in temperature.
Ma'am, we replace alpha with beta.
It's beta, boys. In the previous case, it was alpha.
Ma'am, should we write the formula also?
No. We have to derive the formula. Once you have completed, please answer. Shall I go for the next one?
Yes, ma'am.
Yes, ma'am.
One second. Sorry, you are going to derive an expression for the superficial expansion, and then you're going to define coefficient of superficial expansion. Now, experimentally, it has been found that the change in area is on two things. Right? Change in area, that is delta A, is directly proportional. First one, it is proportional to the original area. If you have a larger original area, then the increase in area will also be more. Second one, it depends upon the difference in temperature, delta T. So I can write, when you combine these two together, delta A is proportional to A1 into delta T. Clear, boys? I'm removing the constant of proportionality and bringing, I'm removing the sign of proportionality, bringing a constant of proportionality, that is beta. So this beta, we call it as coefficient of superficial expansion. This gives you an idea to what extent the area of the material can expand. Coefficient of superficial expansion so beta becomes equal to delta A divided by A1 into delta T. Clear, boys? Is that clear? Kavin, Harish? Kavin,
Yes,
Harish?
Yes, ma'am.
Now we need to define, boys, I have to define beta. For that, what we will do is, let your initial area be 1 meter squared. The increase in temperature be 1 degree centigrade. I'm applying these conditions. Your initial area be 1 meter squared. The increase in temperature, let it be 1 degree centigrade. Then what happens to beta? Beta becomes equal to delta A. Are you clear, boys? Now look at the definition. Coefficient, beta is coefficient, sorry. Beta is coefficient of superficial expansion, right? The coefficient of superficial expansion is defined as the increase in area, boys. Which is your increase in area? Delta A is your increase in area. Are you clear, boys? The coefficient of superficial expansion, beta, is defined as increase in area. Now comes the condition. Increase in area per unit area. Which is per unit area? This one. Per unit area, which means your original area is 1 meter square. Per degree rise in temperature, which is per degree rise in temperature, delta T. Are you clear? Are you clear, boys? What is beta? The coefficient of superficial expansion is the change in area, delta A. Delta A is increase in area or change in area when for unit initial area and per degree, which means delta T should be 1 degree Kelvin or 1 degree centigrade. A1 should be 1 centimeter squared, 1 millimeter squared, or 1 meter squared. It should be unit area. Then beta becomes equal to delta A. That is nothing but increase in area. So this is how you define your coefficient of superficial expansion. What is the SI unit? Can someone tell me what will be the SI unit of beta, even for that case alpha also?
Ma'am, is it per Kelvin, per degree Celsius?
Per Kelvin, yes, correct. It is per degree Kelvin or it is per degree centigrade, because look at the expression. delta A and A1, they have the same unit. It's the area of unit. Meter squared will get cancelled. So what is left? If I'm going for the
Kelvin.
SI unit, meter squared by meter squared degree centigrade. So this will get cancelled. So C to the power of -1. So area is always, sorry, unit is always per degree Kelvin or per degree centigrade.
Ma'am, should we write let A1 equals to 1 meter square and delta T equals to 1?
Yes, you have to. Otherwise, you can't define those. Paper said given to supervisors. Both the sets I have told her that I have already kept this post. Did you complete, boys?
Yes, ma'am.
So next we'll go for cubical expansion. Should I put this in the chat box? 11B, should I put the slide in the chat box?
Ma'am, I'll do it, ma'am. I did.
Okay. Next one. Right, boys. Next one, cubical expansion. Same way, for cubical expansion, you are considering the material in the form of a cube. I'll ask someone to initialize. Jonathan?
Yes, ma'am.
Okay, Jonathan, can you, okay, always white doubling Jonathan. Let others also. Nabil?
Yes, ma'am.
Nabil, initialize whatever you are looking onto. So you have a solid cube.
Yes,
Initialize. Initialize the condition. What is V1? What is T1? What is V2? What is T2?
So when we talk about V1, it's the original volume
Okay.
that happens on
Fine. Okay.
before cubical expansion. And change in
Okay,
volume
fine.
is how much changes occurred since the real volume and the final condition. Change in temperature, what temperature has been reached in order to make this happen, and coefficient of
Sure.
cubical expansion. Yeah.
Gamma. Okay. Thank you, boss. So you have a material in the form of a cube. The initial volume of the cube is V1. It was at a temperature T1 degrees centigrade. You're supplying heat energy so that the material expands. It's a volume expansion. The material expands so that its final volume is V2. It reaches the temperature T2. So the change or the increase in volume delta V is V2 minus V1, and its increase in temperature or change in temperature is T2 minus T1. So then the coefficient of cubical expansion is gamma, for which we have to derive an expression. So just write the initial condition by yourself, boys. V1 is the original volume of the solid cube. V2 final volume, delta V change in volume, T1 initial temperature, T2 final temperature, delta T change in temperature, then T2 minus T1 is delta T. Gamma is the coefficient of cubical expansion. Be a bit fast, boys, so that I can complete your chapter most probably by last period.
Yes, ma'am, you can.
Okay, so I'll go for the next slide. In the same manner, you need to proceed, boys. So it has been experimentally found the change in volume is directly proportional, right? It is directly proportional to original volume or initial volume V1. Then second one, it is directly proportional to increase in temperature or change in temperature. So increase in temperature, so that is delta T. Now you combine both. When you combine both, change in volume is delta V. So delta V is proportional to V1 into delta T, or I'm introducing a constant of proportionality, which is gamma. So it will be V1 into delta T, or I can write gamma is equal to delta V divided by V1 into delta T, where gamma is called coefficient of cubical expansion. Right, boys? So now I have to define. So let V1 be equal to 1 meter cube and delta T be equal to 1 degree centigrade. These conditions you are applying, then you will get gamma as delta V. So then your coefficient of cubical expansion is defined as is equal to, what is this, change in volume I need to complete still more the further statement. What are the further statement? What is the further statement that I need to complete? Surya or is Maheshwar? Are you in class, Maheshwar?
Yes, ma'am.
Okay. Is it Maheshwar or Surya? Boss?
Miss Maheshwar.
Maheshwar. Okay, fine. So coefficient of cubical expansion is equal to change in volume. You have to define now. So under what condition, Maheshwar? Under what condition? Coefficient of cubical expansion is defined as the change in volume. Under what condition? What condition? What is the condition? When the initial volume is Maheshwar? When the initial volume
is 1 meter cube and temperature is
1 meter
degree
cube and the rising temperature is 1 degree centigrade. You can put it in your own words, boys. Now you put the statement properly. Can you put the statement properly? The coefficient of cubical expansion is equal to
Change in volume.
change in volume because the denominator means I have to use per. What is 1 meter cube? Unit volume, correct? Per unit volume,
Per unit
per degree
volume,
rise
per
in
degree.
per
Celsius.
degree rise in temperature. Boys, look at the expression and answer. Gamma is equal to delta V by V1 into delta T. So gamma is nothing but coefficient of cubical expansion. It becomes equal to change in volume when the initial volume is 1 meter cube and the rise in temperature is 1 degree centigrade. You can write it in your own words. The coefficient of cubical expansion is equal to the change in volume when the original volume is 1 meter cube and the rise in temperature is 1 degree centigrade. Enough, you can put it in your own words. Are you clear, 11B?
Yes, ma'am.
Yes.
Yes, ma'am.
Fine, boys, you can leave.
Ma'am, for these three derivations, should we draw any diagram like a rod
No
or a
need.
cube?